All right. So we don't have any quizzes this week because of the exams. I commend you all for being here. I know it's really difficult, especially after exams doing Chem 162, to have to take the exam last night and then come here and go back into material. So I commend you all being here. What it's worth. Okay. So anyway, we are going to continue with chapter 17, maybe even finish it. So we're going to talk about two more scenarios, I guess, in aqueous solution that involve equilibrium. Okay. And so on my notes today are some answers to practice problems dealing with KSP and solubility from the other day. Okay. So if you recall, on Monday we ended by talking about the opposite of dissolving something, which is precipitation. So if we mix two solutions together that contain ions, that when you mix them together, two of the ions come together to form an insoluble compound, then we will get precipitation, or the possibility of getting precipitation exists, okay? And so we see that anytime two ions that can come together to form an insoluble compound can come together, you're going to have a reaction taking place in the forward direction. Now, the thing is, though, is that just because the presence of these ions, that's not enough. We have to make sure that they're present in a certain amount or a certain minimum concentration in order for precipitation to actually begin. And that's where we have to figure out the value of Q upon mixing. What's the value of Q between the ions, and compare it to the KSP value for the ionic compound that's going to precipitate out. And we saw that by comparing Q to K, we can predict whether precipitation will happen between two solutions upon mixing. Okay? So if Q is larger than K, you will get precipitation. If Q is less than K, you don't get precipitation upon mixing. And if Q is just equal to K, that's when precipitation will just begin. On the atomic level, you will get precipitation, but odds are on the macroscopic level, to your naked eye, you won't see the precipitation happening, though, in this very specific scenario. But most of the time, Q is going to be larger than K. It's never going to really be equal to K. So anyway, so we saw how we can now predict precipitation based off of the mixing of two compounds, or two ionic compounds. And so now what we're going to do is we're going to look at this technique called selective precipitation. So this is an analytical technique that is used when you have a solution that contains different cations, for example, and you want to know what cations are present in that solution. One of the things you can do is start adding some compound to that solution to try to precipitate out certain cations, okay, while leaving other cations in solution. So this is why we refer to this as selective precipitation. Okay, so when a solution contains different cations, we may want to be separating out the cations based off of their different solubilities. Okay, and so what we might do is add some kind of aqueous solution to this mixture of cations and try to get some to precipitate out. Okay, now in order for this process to be useful, in order for us to be able to do selective precipitation between different cations, the KSP values have to be different from the different precipitates. They have to differ by at least 3 orders of magnitude. All right, meaning that the things that you're trying to precipitate out, they should have very different solubilities. If you have two ions that have very similar solubilities, it's going to be very difficult then to selectively precipitate out one versus the other. So ideally, you want the cations that have vastly different solubilities. So for example, let's say we have an aqueous solution that contains calcium ions and barium ions. Okay? So we have the calciums and the bariums floating around. Now, of course, there's some anion in here that we're not showing. Maybe it's calcium nitrate and barium nitrate. Right? The nitrate is unimportant. What we care about is the fact that we have this mixture of two cations. Okay? And say we want to precipitate out, we want to selectively precipitate out the calcium from the barium. And so we have a choice. We can either add a solution that contains carbonate ions, or we can add a solution that contains fluoride ions. And so by adding one of these two solutions to this, we can form precipitates. Okay? And so to figure out which would be the better choice to selectively precipitate out one versus the other, let's compare the KSP values of the precipitates. Okay? So let's say, for example, we use carbonate, and we want to precipitate out one versus the other using the carbonate solution. So maybe it's sodium carbonate or potassium carbonate. Okay? Well, the calcium carbonate's KSP versus the barium carbonate's KSP. Let's compare the two. So calcium carbonate has a KSP of 4.9 10 to the minus 9, whereas the barium has 2.5 10 to the minus 9. So notice that they have the same stoichiometry, so their KSPs are very similar, so that means that they have very similar solubilities, right? Now compare that to the precipitates you can get with the fluoride. So we could get calcium fluoride versus barium fluoride. Now when we compare the KSPs of these, we see that the calcium fluoride has a KSP of 1 times 10 to the minus 10, whereas the barium fluoride has a KSP of 2 times 10 to the minus 5. Since they both have the same stoichiometry, we can use the KSP values directly to rank their solubilities. And we see that the calcium fluoride is 5 orders of magnitude, so approximately 100,000 times less soluble than the barium fluoride. So because of the fact that there is this really huge difference in solubility between these two compounds, the better choice to try to selectively precipitate out these ions from one another is by using the fluoride solution. Right? Using the carbonate would not be a good way to precipitate out only one of the cations. Whereas this one, when we use fluoride, we'll be able to precipitate out the calcium first before the barium comes out. Now, of course, when you're doing this kind of selective precipitation, the concentration of the solution you're adding is going to be very, very, very dilute, because you don't want to add so much of the fluoride that you precipitate out both of these. You only want to add a little bit of fluoride, tiny bit, so that the calcium will start coming out first. All right, and then once you think that you have all the calcium out, then you can stop, and then you have it separated. Okay, so this is the basis of selective precipitation. Okay, so let me talk about the process a little bit more in terms of conceptually what's happening, and then we'll focus on the calculations that we can do. Okay, so again, let's consider that we have a solution, a 1 liter solution that contains 0.1 molar concentration of lead-2 ions, and we also contain 0.1 molar strontium ions, okay? And to this, we're going to be adding a solution of sodium chromate, okay? Now remember, the sodium is unimportant. What we care about is the chromate, because the chromate can react with either the lead or the strontium to make insoluble compounds. Notice that strontium chromate has a KSP value of 3 10 to the minus 5, whereas the lead chromate has a value of 2.8 10 to the minus 13. So notice that they have very different KSP values, which is really good because that's what we want if we're going to precipitate out one versus the other. So here we have our scenario, right? This is what we're starting off with. Now again, there's some anion here that we're not taking into account. It's unimportant. Right? So initially, before we do our selective precipitation, all that we have is water, and we have lead ions, and we have strontium ions. However, we have not started to add the chromate yet. We haven't started to add the sodium chromate. So now what we're going to do is we're going to slowly add chromate to this solution here in the form of sodium chromate. We're going to slowly add a dilute solution of sodium chromate so that the chromate concentration starts to increase in the solution, okay? Now eventually, the chromate concentration is going to get to a level where we will have enough chromate to start to precipitate out the lead as lead chromate. So it builds up, the chromate builds up, eventually it reaches this point where we're at the right level where we start now precipitating out the lead ions, okay? This is going to happen when the Q, so the Q value, we still have to think about the reaction quotient. The Q value of lead chromate, when this is numerically equal to the K value, KSP value, that's when the precipitation will start. Okay, so again, if you think about what we're starting off with here, we're starting off with 0.1 molar concentration of lead, and then we're adding the chromate. So the concentration of the chromate starts to go up and up and up. Eventually, the concentrations, as we learned last class, will reach the level where precipitation will begin. Okay? All right, and so as we keep adding more chromate at this point, we will be precipitating out more and more of the lead. And eventually we're going to precipitate out pretty much all of the lead, okay? Now, once all of the lead precipitates out as solid, then if we continue to add chromate, now we're going to start to precipitate out the strontium, okay? So we reach this level and we start adding more chromate, then we start precipitating out the strontium chromate. Now again, this is going to happen when the Q value for strontium chromate is equal to its KSP value. When they're numerically the same, that's when the precipitation will begin. And the more that we add chromate, the more we'll be able to precipitate out the strontium then. Okay? Now notice that the first one that came out was the lead. right? Because the lead, if you look at the KSP values, lead has a much lower solubility than the strontium does. So that's why that's going to be the first one to precipitate out. Okay? So I just want to make sure we understand the concepts here. Okay? Any questions about concepts? We are going to do now a whole bunch of calculations based off of this to figure out what the concentrations need to be to cause this. But before we move forward, does anybody have any questions about, well, what do I mean by selective precipitation? What we're actually doing here? Because this is actually a technique that still is used in labs. When, like, for example, if you have a sample of water and you want to figure out what contaminants, what ions are in there, you can use precipitation reactions to do that. Okay, so any questions conceptually so far before we move forward? Okay, so now let's start talking about the numbers. Let's talk about how much chromate has to be put in order for the precipitation to begin, and all these different things. So let's consider again, 1 liter solution, right? We have 0.1 molar lead and 0.1 molar strontium, and we're going to start adding that sodium chromate. So the first question that comes out is, well, why does the lead precipitate out before the strontium? Now, I already kind of mentioned this, but let's prove to ourselves that this is the case. So why is the lead coming out before the strontium? So what we want to do is we want to calculate the amount of chromate, the concentration of chromate that's required to precipitate out the lead, and compare that to the concentration of chromate needed to precipitate out the strontium. And let's see if there's a difference in the amount of chromium needed, or chromate needed to do that. Okay? And so remember, we are going to use the fact that precipitation of one of these solids will happen when its Q value is equal to its KSP value. Okay, that's the thing that we want to be paying attention to. So if we start off with a solution of lead that has a concentration of 0.1 molar, and we want Q to equal KSP, so this is what we're going to now calculate, is what's the initial concentration of lead, and what does the initial concentration of the chromate have to be, so that when you multiply the two and you get its Q value, it will numerically equal the KSP value, because that's when precipitation begins, right? So we know that we are starting off with 0.1 molar lead, and we want to see what does the chromate have to be so that we'll get precipitation. So we solve, and we see that in order to start precipitating out the lead, the concentration of chromate required is only 2.8 times 10 to the minus 12 molar. So you do not need a large concentration of chromate in this circumstance to get the lead to start coming out of solution. Okay? Now, let's compare the amount of chromate needed for the strontium to come out. So now we'll focus on the strontium. Same situation. The strontium will start precipitating out when its Q value equals its KSP, right? And so again, we have the initial concentration in the solution is 0.1 molar, and we want to figure out what does the chromate have to be so that this will start precipitating. So Q has to equal KSP. So we solve, and we see that the chromate concentration needed to precipitate out strontium is 3.6 times 10 to the minus 4. So take a look at the difference in concentrations required to cause precipitation. We only need 10 to the minus 12 molar to precipitate out the lead, whereas we need 10 to the 4 molar to precipitate out the strontium. You're talking 8 orders of magnitude difference in terms of the concentrations. This is the reason why the lead will precipitate out before the strontium does, because of its KSP being so much smaller. Okay? So this is, again, why we can maybe understand why if we want to be able to separate two ions, we have to choose precipitates that have vastly different solubilities, right? Because if they have similar solubilities, then this concentration of chromate is going to be enough probably to precipitate out both of them at the same time, which totally neglects the purpose or negates the purpose of what we're trying to achieve there. Okay? So does anybody have any questions about, yes? So the one that has the lower KSP, so the smallest KSP, is less soluble, so that one will be the one to precipitate out first, right? And again, we want our precipitates to have different KSPs by at least 3 orders of magnitude. Here we have 8 orders of magnitude, so it's totally fine. Okay. Any other questions about how we figured out these calculations here? Yes? How do you know the concentration of the cation? I missed that last part, sorry. Because we're trying to figure out, so remember that precipitation, it's all based off of the KSP reaction, right? So if we remember, so for example, let's see. So let's talk about the lead. So PB, 2 plus, let's do PB, PB, we're doing chromate, right? Okay, so PB CrO4 solid in equilibrium with PB 2 plus and chromate CrO4 2 minus aqueous, right? So let's think about if we're doing an ice table, for example. We're starting off with a concentration, we're starting off with a solution with a concentration of 0.1 molar lead, okay? So initially, well, I guess the thing is that what we want to do is we want, so this is going to be 0.10, we want Q to eventually be larger than K, because when Q is larger than K, which way will the reaction go? It will go to the left. So we want the chromate concentration to be high enough so that when we figure out the value of Q, now notice the value of Q is based off of this reaction, right? Q is equal to the lead concentration initially times the chromate concentration initially, right? We're basing it off of this reaction here. So when Q is larger than K, the reaction has to go in this direction to reestablish equilibrium. So that's why we're figuring out the Q value the way that we are. Does that help? Good. All right. Other questions? Okay. All right, so now we've established why the lead will come out first before the strontium. Now let's figure out, okay, when the strontium, remember the strontium is the second one to precipitate out. So when the strontium starts to precipitate out, what's the concentration of lead ions still floating around in the solution? How much of the 0.1 molar lead did we actually precipitate out as solid? Did we only decrease the concentration from 0.1 to maybe 0.05? Or did we decrease the concentration of the lead a more appreciable amount? Did we really selectively precipitate one versus the other? That's what we want to establish. So when the strontium starts precipitating out, how much lead, free lead, is just floating around there, right? And so what we're going to do is use the fact that when precipitation will occur for the strontium, the chromate concentration has to reach 3.6 10 to the minus 4. We established that with the previous slide. So when chromate concentration equals 3.6 10 to the minus 4, that's when the strontium will start coming out as a solid. At this concentration of chromate, what's going to be the concentration of the lead still floating around? And now what we're going to do is just simply solve for our KSP value, right? So really what this question is asking for is what's the equilibrium concentration of lead when the strontium starts coming to a solution, or when the chromate concentration is this value here, 3.6 10 to the minus 4. So what we're going to do then is just plug our values in, right? So the concentration of lead is what we're solving for. The chromate concentration has to reach this value for the strontium to come out. And we still have to have this times this equals our KSP value. So when we solve for our lead concentration, so originally we had a 0.1 molar concentration of lead. We precipitated it out, and then once the strontium starts coming out, this is how much lead is remaining in solution. We started off with 0.1, now we're down to 7.8 10 to the minus 10 molar. So the lead, so this is how much lead we precipitated out essentially. We essentially, for all intents and purposes, precipitated out all of the lead ions before the strontium even starts to begin precipitating out. All right? This amount of 7.8 10 to the minus 10 it's ridiculously small. So for our purposes, there's hardly any there. Okay? So here we see that we were totally successful in selectively precipitating out lead versus the strontium. So these are the kind of calculations, numerical kind of calculations you're going to be expected to understand when it comes to selective precipitation, all right? Knowing these kind of concentrations, what's the concentration of this one ion when the other one starts precipitating? What does the concentration of this have to be so it precipitates out with that, etc. Okay? Any questions about calculations? I know, again, this is probably not what you want to see after last night, but got to do what got to do. It's good. All right. Okay, so this is selective precipitation, and now what we're going to do is we're going to talk about, again, things that we can do to our solution to increase the solubility of something. Now, we kind of touched on this the other day. I'll give you some practice problems to try on your own dealing with the stuff we were just talking about. Okay, so let's say that we want to understand how we can increase the solubility of an ionic compound, right? So for example, the lead chromate, when you put it into water, it's highly insoluble. Is there something I could put into the water to make the lead chromate even more soluble, right? That's really what we're asking here, right? So we can increase the solubility of an ionic compound in relation to the pure water if that compound contains an ion that can react with something in the water, right? And so if you remember, we talked about this the other day on Monday. So according to Le Chatelier's principle, if there is something in the water that can react with one of the ions in our compound, that will effectively take that ion out of commission. And according to Le Chatelier's principle, more of the solid will therefore try to dissolve to reach equilibrium. Okay? And so we saw this when ionic compounds have a basic anion. We saw that we can increase the solubility of that ionic compound by putting the ionic compound into acid. Because what happens is that the acid, so if we consider, yes, so if, let's say we want to talk about the solubility of aluminum hydroxide, okay? Now this is insoluble, it has a very large KSP, or actually a pretty small KSP. And say we want to make more aluminum hydroxide dissolve in the water, okay? So if there's something that we could put in the water that will either react with the aluminum ions or react with the hydroxides, then according to Le Chatelier's principle, if we can lower the concentration of one of these, then in response to that, the reaction will go to the right to make up for that, and more solid will dissolve, right? So when we add the aluminum hydroxide to acidic solution, what's going to happen is the H pluses in the acid are going to react with the OH minuses here to form water, which essentially will decrease the concentration of hydroxide and cause the reaction to go more to the right to reach equilibrium, right? So we see this this is a strongly basic anion, but we can see the same effect with weak base ions. So like fluoride or nitrite or acetate or cyanide or something like that. Okay, so we saw this with the anion. So this effectively decreases the concentration of hydroxide, and in response to that, more aluminum hydroxide will dissolve. So this was something that we could do because of the ion, the anion. Let's take a look at a different situation though. So let's say we want to consider silver iodide, AgI. Again, it's another pretty insoluble ionic compound. It has silver ions and it has iodide ions. So the first question that comes up is, say I want to increase the solubility of silver iodide with respect to water, and we want to use pH. Well, we're going to see that adding this to an acidic solution will not impact the solubility. Well, again, think about why that is. So if we're adding this to acid, there's a whole bunch of H pluses. Will the H pluses react with the iodides to make HI? No, because HI is a strong acid. It will always be dissociated. So in this situation, because the iodide ion is not basic, right? It's totally neutral. It will not cause the reaction to go more to the right in response. Okay? So we cannot increase the solubility of the silver iodide by using pH. However, the question comes up, well, I can also increase the solubility of the silver iodide by getting rid of the silver ion. So is there something I can do to the water to cause the silver to get reacted and to turn into something else, so that when this concentration goes down, the reaction will go more to the right to reach equilibrium? And it turns out that yes, there is going to be a way that we can get rid of the cation, all right? And so this is called complex ion formation. So this is what we're going to be doing. This is one of the things we can do to our solution. Have something in the solution that will form a complex ion with our cation. Okay? So first of all, let me define what exactly is a complex ion. So it's essentially a reaction between a Lewis acid and a Lewis base. So you have a metal cation, right? So it's a metal that has a positive charge. The metal cation is going to act as a Lewis acid. It's going to accept lone pairs. It's going to accept lone pairs from a Lewis base, who's going to donate the lone pairs. Now in this case, we refer to the Lewis bases, we refer to it as a ligand, okay? So the coming together of a Lewis acid and the Lewis bases will form this thing called a complex ion, okay? So a complex ion is always composed of the same components. You have some central metal cation, all right? And then you have one or more ligands bound to that central metal cation. Now the ligands, like I said, are Lewis bases. They're lone pair donors. So something that has to have a lone pair on it, okay? And so we can get then the formation. Now the ligands that are going to bond to the central cation, they might be charged, they might be negative charged, or they might be neutral. They can be monatomic species or polyatomic species, okay? And in fact, on Monday, when we talk about chapter 22, we are going to get into more detail about complex ions, what they are, how they form, okay? So we're going to come back to this more in chapter 22 on Monday. But essentially what I want you to realize is that a complex ion is just pretty much a polyatomic ion on steroids. You got a central cation with a whole bunch of things attached to it. The entire thing has a charge to it, okay? So for example, if I put silver ions into a solution with ammonia, well, these two will form a complex ion, and you get the following reaction, where the silver cation reacts with two molecules of ammonia to form this thing. This is the complex ion, okay? So the silver is acting as our central cation. That is our Lewis acid. That's going to be the lone pair acceptor. The ammonia, that's our ligand. That's going to be the Lewis base. That's going to be the thing that donates the electrons to the central metal cation. They come together and they form bonds, so you form this complex ion. So you have a central silver with two ammonia molecules attached to it, and the entire thing has a charge to it. That's why we refer to it as a complex ion. Now notice that the formation of a complex ion is an equilibrium process. So you put these things together and they will all come into equilibrium with one another. You'll form complex ion, but then you're going to have some of these still remaining because it reaches equilibrium. Notice that it has a K value associated with it. And notice that the K value has a very special subscript. Since this is the K value for the formation of a complex ion from its components, we call this K value Kf. So it's called the formation constant for the complex ion. So it is a special value of K, just like Kw gave you a very specific reaction. Ka referred to a very specific reaction. Kb referred to a very specific reaction. Ksp referred to a very specific reaction. Kf refers to a very specific reaction. But these are all Kc values, right? They're all just equilibrium constants based off of concentration. Okay? So the rest of this slide at least is chapter 15. So we can then figure out the value of our Kf for a certain formation of a complex ion by using the aqueous species, right? So if I know the concentration of my complex ion at equilibrium, and if I know the concentration of the silver and the ammonia at equilibrium, I can use those values to figure out my Kf value, right? Just like we learned, it's by the reactants, okay, raised to their powers. So we see here that the formation constant, at least for the silver and the ammonia, we have a pretty large value of 1.7 10 to the positive 7. So when you put silver in the presence of ammonia, how much do they like to form the complex ion? They love to form the complex ion. When they can get together, they're going to, okay? So we see because of the K value being so large. Okay? So this is what we mean by complex ion formation. It's just yet another equilibrium process that's happening in water. All right? And it has, again, another special K value that gives you the context, gives you the reaction. Any questions about this? So it's just more of the same, unfortunately. Okay? Okay, so this was just one complex ion. If we take a look now, remember from chapter 16, this is the first time where we actually talked about complex ions. And this was in the context of aluminum. We said that small, highly charged cations can be acidic, right? And we were like, well, how is that possible? And it's because small, highly charged ions can form complex ions with water. So the water is actually acting as the ligand. The water acts as a Lewis base. The aluminum is acting as the Lewis acid. They come together to form this complex ion. And then one of the protons, excuse me, on the complex ion can now be acidic. and it can lose it to the water and forms another complex ion. Right? So we already kind of saw complex ions last in chapter 16. Right? But now we're going to focus on more complex ions, so not just aluminum and water, not just silver and ammonia. So here's just a small, example of different complex ions that can form. Okay, so we have different essential metal cations that might be silver, could be copper, iron, cobalt, etc. We can have all these different ligands. So for example, cyanide or ammonia, this is thiosulfate, fluoride ions. We'll talk more about the ligands on Monday. But the thing that I want to bring out about all of these complex ions is look at the Kf values. So we have 10 to the, so the smallest one here is 10 to the positive 8. And the largest one here is 10 to the positive 43. And so this is something really important to recognize. If complex ion formation can occur, it will occur because the K values are so high. Okay? So we have relatively large K values, so that means we're going to be able to use the large K approach when we're dealing with complex ion formation, because the K values are so big. Okay? And so we should be able to identify the species. So if I give you a K value for something like this, you should be able to identify this as being a complex ion. You should recognize that first of all this has a charge to it, so that's what makes it an ion. But furthermore, you should recognize that you have a metal and then a certain number of ligands attached to that, right? And so if I give you the Kf value for aluminum AlF63-, let me say, I say that the Kf for this species is, oh, I'm sorry, there's two, but there was only one. All right. So let's say I tell you the Kf value for this is 7 times 10 to the positive 19. You should then be able to write the reaction that this is referring to, right? So it's Al3 plus 6 F minuses to form the complex. Right? So if I give you the chemical formula of the complex ion, you should be able to write the formation reaction from that. Okay? Is that clear? Any problems with that? Okay, so now we see that these things called complex ions can form under certain circumstances. So what? Well, remember, what we were trying to do here is we were trying to talk about how we can increase the solubility of something, right? And we focused on the silver. So let's go back now to trying to increase the solubility of the silver iodide. Now, we already said that we won't be able to increase the solubility of the silver iodide because of the iodide ion, right? Because it doesn't have any basic properties. But is there something we can do to that silver? So, since silver ions form a complex ion with ammonia, well, that means that if I put silver iodide into ammonia solution rather than water, the silver iodide is going to have a much, much larger solubility in the ammonia solution because the silver can form a complex ion with the ammonia. And so remember, what that's going to lead to is that's going to cause the concentration of the silver to go down, which will then lead to more AgI dissolving in that solution, according to Le Chatelier's principle. Okay? So really what we have then is that when I put the silver iodide into a solution of ammonia, I actually have two processes happening at the same exact time. Okay? One thing that's happening is that we have the silver iodide dissolving in the water of the ammonia solution, right? So the silver iodide solid starts to break up into the silver ions and the iodide, right? And this reaction has a K value of KSP, right? And then we also have now the complex ion formation, that when the silver ions are then formed, they can then react with ammonia in the solution to form your complex ion. And so this reaction here has a K value of Kf. So when we add these two reactions together, so again, what we're doing is we're putting silver iodide into a solution of ammonia, not water. Okay? And this is what happens overall. Notice how the silver ions cancel each other out in the overall reaction, and this is the net result that's happening. I'm putting the silver iodide solid into an ammonia solution. I'm forming a complex ion and also iodides. Now, this is also an equilibrium reaction. It's the combination of these two equilibrium reactions. So if I know the K values for each of these, how do I figure out the K value for the overall reaction? I'm just going to multiply KSP by KF. And this will give me the K value for this reaction here. Okay? And so we multiply KSP by KF, and we see that we have now a K value of 1.4 10 to the minus 9. So by knowing the K values for each of these individual reactions, we can put them together to come up with the overall solubility reaction of an ionic compound in a solution where there's a ligand that will form a complex ion with the metal. Okay? Any questions again about what we're doing here? Okay? So again, our job here, what we're trying to do right now is we're trying to establish that by putting the silver iodide into an ammonia solution, it's going to be more soluble than if we just put the silver iodide into water. And I'll prove it to you in a second. Yeah? Right, so I'm not just putting this silver iodide into pure water, I'm putting it into an ammonia solution. So it's not like that's a small change. You know, that's a pretty drastic change. But we're just trying to show how we can change the solubility of something. Okay, so now let's prove to ourselves that this is going to increase the solubility of the silver iodide. Okay, and so now let's compare the solubility of silver iodide in two circumstances. We're going to compare the silver iodide solubility of pure water to the solubility of silver iodide in a 2 molar ammonia solution. Okay, and so since we want to know the solubilities, what do we have to do? We have to set up an ice table and we have to solve for S, right? So let's do that. Okay, so two different circumstances here. Okay, so first thing I want to do is figure out the solubility of silver iodide in pure water. So that means that I'm just going to do my KSP reaction. So I got AgI solid in water, which I'm not going to write just because of space. So that's going to come into equilibrium with Ag plus, aqueous, and I minus, aqueous, right? And so ICE. Again, you can memorize the fact that KSP is equal to S squared here, or you can just do the ice table, right? So we start off with an initial amount of silver iodide in the water. We don't care about the initial amount. Before the silver iodide starts to break up in the water, there's 0 molar of Ag plus and 0 molar of iodide. So we know that the reaction has to go to the right to reach equilibrium. So a certain amount of the silver iodide is going to dissolve. We call that amount S. That's the thing we're solving for, is this value of S. If this goes down by S, the silver will go up by S, and so will the iodide. Will also go up by S. So that at equilibrium, it's going to be S and S. So our KSP value for silver iodide is going to be the Ag plus concentration at equilibrium times the concentration of the iodide at equilibrium. And since this is S and this is S, we now have that the KSP value is going to be equal to S squared. Now the KSP for silver iodide, we look it up. It was on the previous slide, and it turns out that it's 8.51 times 10 to the minus 17. So now we're going to solve for the molar solubility of silver iodide in pure water. So we're going to just take the square root of 8.51 10 to the minus 17. 8.51 10 to the minus 17. Shoot. 10 to the minus 17. Take the square root of that. Okay, and I see that the molar solubility of silver iodide in pure water is 9.22 times 10 to the minus 9 molar. Okay, so in other words, if I have one liter of water and I put silver iodide in it, only 1/1 of a mole of silver iodide will actually dissolve in that water. So very insoluble, right? Now let's compare the solubility of the silver iodide in a solution of ammonia, not pure water. Okay, and so now for this situation, remember, we're going to use the overall reaction here of AgI solid plus 2 ammonias, right? So we established this from the previous slide. We're going to form our complex ion, which I'm going to run out of room here. So Ag, NH3, 2. And we're also going to form iodide, right? And so remember, the iodide is aqueous, the complex ion is aqueous, the ammonia is aqueous, and the silver iodide is a pure solid. Okay? So now let's do our ice table and figure out the value of S here. So ICE. Now again, we don't care about the initial amount of silver iodide solid, so don't worry about that. Now, before I put the silver iodide into the ammonia solution, do we have an initial concentration of ammonia? Yes, we have an initial concentration of 2 molar. So in my ice table, this is going to be 2.0 molar. Initially, before the ammonia reacts with the AgI, the initial concentration of our complex ion is 0, and the initial concentration of our iodide is 0. So a certain amount of the silver iodide has to dissolve here. So for our change line, this is going to go down by S. This is going to go down by 2S, right? So ammonia goes down by 2S. This complex ion will go up by S. and the iodide will also go up by S. Now remember, we're trying to solve for the value of S, the molar solubility here. So at equilibrium, again, we don't care about the silver iodide solid. The ammonia is going to be 2.0 minus 2S. This is going to be S, and this is going to be S. Now I'm going to plug this into my equilibrium expression. So the K value for this reaction, remember, it's going to be the concentration of my complex ion at equilibrium times the concentration of the iodide at equilibrium divided by the concentration of the ammonia at equilibrium squared. So let's plug our values in. And this all has to equal our K value. Now remember, on the previous slide, just to prove to you again, we came up with the K value for this overall reaction here. So it's 1.4 10 to the minus 9. We established that already. Okay, so let's put that in. So it's going to be 1.4 10 to the minus 9. And now we're going to plug our values in. So the silver concentrate, sorry, the complex ion is equal to S, and this is equal to S. So it's going to be S squared. The ammonia is going to be 2.0 minus 2S quantity squared. And this is all going to equal 1.4 times 10 to the minus 9. Remember, our job here is to solve for S, okay? Now notice that my K value here, which is a combination of Kf and Ksp, it's not just one by itself, it's both of them put together. It's 10 to the minus 9, so it's still a small K value. So what does that mean mathematically? That means I can make my small K approximation here. I could say that the value of 2S is so small compared to that 2.0 that I'm going to neglect it. Okay? And so what I'm left with now is the following. S squared over 2.0 squared equals 1.4 times 10 to the minus 9. Now I'm going to solve for S. So S squared is going to be 1.4 10 to the minus 9 times 4. 10 to the minus 9 times 2 squared, which is 4. So S squared is 5.6 10 to the minus 9. And then S, which is our molar solubility of silver iodide in the ammonia, is the square root of that, which we get to be 7.5 times 10 to the minus 5 molar. Okay, so now we've calculated the solubilities of the two different compounds, or the same compound in two different environments, the water versus the ammonia. Now look at the difference in solubilities here. The solubility for the water is 9.2 10 to the minus 9 molar, whereas for the ammonia, even though that's still not a huge solubility, compare that though to the water. This is still 4 orders of magnitude more soluble in the ammonia than in the pure water, because what happens? The silver in the silver iodide can make a complex ion with the ammonia, and that will therefore, according to Le Chatelier's principle, that's going to increase the solubility of it. And so we see that the silver iodide is about 8,000 times more soluble in ammonia than in pure water because of this formation of complex ion. Okay? So now we see that if we put it all together, we can increase the solubility of an ionic compound either by having an anion that's basic and we put it in pH that's acidic, or if the cation can form a complex ion with a ligand, we could put it into a solution of the ligand and we'll increase its solubility also. All right? So take a moment to consider this, make sure if there's any questions about what we just did here. And more ice tables. All right, so the last thing that we'll talk about in this chapter is kind of a combination of this idea, and we're going to talk about these things called amphoteric metal hydroxides. That kind of seems like maybe like a contradiction, okay? Now remember what it means to be amphoteric. Something is amphoteric when it can either act as an acid or a base, depending on what it's being mixed with, right? So water can be amphoteric, it can lose a proton to something, or it can gain a proton from something, right? So water can act as an acid or a base. Well, we actually have metal hydroxides that are amphoteric, meaning that under certain conditions, they can act as acids, in certain conditions, they can act as bases, okay? So amphoteric species can act as either. Now, all metal hydroxides, since they have hydroxide in their formula, of course, all metal hydroxides, please stop talking, all metal hydroxides, no, I'm pointing at you, I'm talking to you and her. I guess you're not recognizing, I'm pointing at you. People don't want to hear you talking. Also in the back too, people don't want to hear you talking either, okay? Go to the student center, get a cup of coffee, it'll be much more enjoyable, have a nice conversation, right? Okay, so, that's why they pay me the big bucks here at Rutgers to keep order. All right, so the so the metal hydroxides, since they have OH minuses in them, that's why they can act as bases, obviously, right? So there's nothing weird about that. So even if the hydroxide is insoluble in water, if you put that metal hydroxide into an acid solution, it's still going to neutralize the acid. It doesn't have to dissolve to do that because of the presence of the OH minus, okay? However, aluminum hydroxide can also act, so this is the reaction that takes place between aluminum hydroxide and strong acid, right? So the hydroxide will still react with the H pluses to form water, and then you're going to be left with just the aluminum ion floating around. Okay? So here's how the aluminum hydroxide is acting as a base. No big deal. Now what happens if the metal hydroxide, it can also act as an acid. Now specifically though, it's going to act as a Lewis acid. And aluminum hydroxide will act as a Lewis acid when it's under basic conditions. So rather than there being a whole bunch of H pluses, there's going to be a whole bunch of OH minuses in the water. Okay? And under that circumstance, the aluminum hydroxide can act as a Lewis acid. So what happens is that the metal hydroxide has to contain one of these ions. So for example, chromium 3+, or zinc 2+, lead 2+, tin 2+, there's a whole bunch of them. Aluminum 3+. So when you have metal hydroxides that have these central cations, they can act as Lewis acids. And they can form complexes with the hydroxides to form a complex ion. So here's the aluminum hydroxide, but now it's under basic conditions. So we have a lot of OH minuses floating around. Under this circumstance, the hydroxide is going to act as a ligand with the aluminum hydroxide. The aluminum is still going to act as a Lewis acid. It's going to make a bond with the hydroxide to form our complex ion. Since the complex ion is soluble, that's going to cause the aluminum hydroxide to dissolve more. So again, it's under basic conditions. Now when it's under neutral conditions, then aluminum hydroxide is highly insoluble. Okay? So the aluminum hydroxide here is acting as a Lewis acid, a lone pair acceptor. The hydroxide here is acting as a lone pair donor, or a base, Lewis base, and we form our complex ion this way. So what we're looking now from now on, when we see hydroxides, metal hydroxides, if the hydroxide has a metal cation that's highly charged, like 3+, a lot of them are 3+, even though I'm giving 2+. Not sodium hydroxide, not potassium, not any of the strong bases that you memorized. Then if you see these metal hydroxides with small cations, odds are they can be amphoteric. Odds are they're going to be able to make complex ions with hydroxide to form a complex. Okay? How did we know this? We didn't know this until we learned this. We wouldn't have known this beforehand. Okay? So any questions about, again, amphoteric metal hydroxides? Right? Fascinating, right? All right. So now, yeah. So we can at least start talking about this last question here. So, you know what? Okay, so I had an exam yesterday. So just try this on your own. I'll put this in my notes. Okay? If you have questions, come see me. Have a good one.